everybody. We're Team Bits and Bytes, and today we'll be giving you our presentation on logic locking using SFL HD0, which we've been doing throughout the semester for ECEN 426. So on today's agenda, we'll first introduce the team, talk about some motivation behind this project, as well as some key background to understanding what we're doing, as well as the methods we use to implement this and results, and then at the end, we'll sort of give a high-level conclusion. As for the introduction for our team, we have Jack Campbell over here. I'm Erin, this is Alberto, and this is David, and we've been the four main people that have been working on this project.
So a little bit of motivation behind why we use logic locking. In IC manufacturing, a lot of the actual manufacturing part is outsourced to third-party facilities, which we can't guarantee the security of. And so we want to protect the intellectual property of those chips. And so what we do is we obfuscate the design so that it's not known by the manufacturer unless a correct key is given to kind of unobfuscate it. The only thing is with regular logic locking, it's not very well, does not do very well against SAT attacks, removal attacks, and sensitization attacks. And so there's a need for a more resilient logic locking, which is what this project is about, SFLL HD0.
So a little bit of background so you can understand what we're talking about when we talk more in depth about our logic locking. A basic definition of what logic locking is it's a hardware defense strategy that embeds additional logic gates within post-logic synthesis step into a circuit design, which locks the intended operation of the circuit with a secret key. The way that we would evaluate this and validate it against threats would be using a threat model, where it assumes that an attacker has an oracle or reverse engineered netlist of our circuit and can identify key input locations on the log netlist. So what is SFL-LHD0? It stands for strip functionality logic locking with a Hamming distance of 0. It's a type of SFLL that inverts the output for a single input pattern. The modified circuit only will operate as intended when the user key matches the correct protected input pattern, essentially meaning that when an attacker puts in the incorrect key value, he won't know if the output is correct or not because he doesn't know the output. So it'll only work whenever you put in the exact key value that we need from the protected input pattern. Here's an example of a block diagram using SFL HD0, where the input to our circuit's on the left. It goes through the logic that we implement for SFL HD0, and then eventually on the right, it will give the output depending on whether the key or the input key that the user used matches the pip value. So a few reasons why we'd like to use SFL HD0 is that the incorrect key guess by any attacker will prompt a secondary output error. It is also very good at defending SAT attack, sensitization attack, as well as the removal attack, and the circuit output will change with each incorrect guess.
Right, so diving into a little bit of the methodology behind our project as well as some of the results, we actually did two different sort of simulations for this. The first part was on benchmark circuits from ISCUS, and the second part was logic locking of a processor. So this is a high-level overview of sort of what we did for the first part on those benchmark circuits. So we start with a benchmark circuit and convert it to Verilog, and then we take that Verilog circuit and convert it to a locked Verilog circuit. We then take that circuit and synthesize the design and obtain a netlist, and then from that netlist, we convert it back to a benchmark circuit that will now be locked. So this is sort of the methodology we did to sort of go through those steps. So first, to convert the bench file to Verilog, we used ABC tool by UC Berkeley in order to convert the left image into the right image. So converting a .bench file to a .b file. And then next, we took the Verilog file and converted it to a locked Verilog file by creating a Python script, and it generated a random protected input pattern. So on that right picture, you can see that our randomly generated pip is 10000. And then with that locked Verilog file, we synthesized the design using the Synopsys design compiler, which simplifies the logic and then generates the netlist. And then with the netlist, we created another Python script to convert the synthesized netlist into a bench file to compare the original bench circuit with the locked bench circuit.
So verifying our methodology, we use the LCMP tool to compare the expected user key with the pip that we find inside the circuit. So starting with our small circuit C17, we input the correct key of 00011, and the tool outputs that the two keys are equivalent. And if we input an incorrect key, such as 00000, the tool says they are different, meaning that our methodology was correct and our implementation was as expected. So we also did this for much larger circuits. Next size up was C432. We input a much larger key, and the tool still is able to output an equivalent key and pip. And if we input an incorrect key, says they're different. And for our largest circuit, C5315, we input a much larger key than before, and it still has the same behavior, indicating that we implemented it correctly. And it's scalable to larger circuits. We also performed the SAT attack on C17, and this was solved in about 17 iterations, which is just a matter of seconds, and it was immediately able to pull the key, which this just means that SFL HD0 is not effective for small circuits.
So moving on to the implementation for the processor design, we are specifically locking part of the decoder logic within the processor. So this is the original processor design with no locking implementation. So in the decoder, we have some generative logic that a variable or function will use throughout the code. And then, however, we'll do the processor with SFL HD0 in this case, which will give us a locked version of whatever variable that we're going to use. So we'll take the instruction and compare it to the expected key, which will then XOR with the original input, which will give us our FSC. And then we will XOR the FSC and then the comparison of the instruction and the user key to get the output for our logic. So sort of the methodology behind the locking for SFL HD0 for this processor, we are locking the illegal instruction functionality on a specific instruction. And if the user key is correct, this instruction should be executed. But if the user key is incorrect, the instruction should not be executed.
And to verify our implementation again, we run a simulation of the processor. And as Aaron just said, if we input the correct key, the instruction will show up in the log files, and you can see the highlighted log file on the left, indicating that it has ran with the correct key. And on the right, you see the instruction does not appear, meaning that it did not run.
So wrapping everything up, some of the pros of the SFL HD0 is that it is resistant to some well-known attacks against intellectual property piracy. It's also really good at scaling up as the actual effectiveness of the method actually grows exponentially as the circuit gets bigger and the key size is larger, which of course leads to better security. Some disadvantages, however, are that in theory, an attacker could guess that key, but is not very likely, especially with a larger key size. It's also not very effective against smaller circuits, as was seen with the C17 circuit. And another disadvantage is that the designer must know where to implement this locking as part of the design. Some of the lessons we learned are what a benchmark circuit is, how to implement the actual logic locking on a bench circuit with some scripts, as well as how to implement this on an actual real-life processor. We also got some better understanding of Verilog, as well as how to use some tools like ABC to convert the bench file to Verilog, how to use Synopsys to actually synthesize the Verilog, and then how to confirm that our locking was working correctly with the LCMP. Thank you.
Thank you.
Thank you.